Hola, ¿cómo están? Soy Pablo, bienvenidos al canal de Físico. Este video va a ser un poquito distinto respecto a los típicos del canal, debido a que, yo soy estudiante de doctorado en Física y tenía que asistir a un congreso de Microfluídica en Córdoba, Argentina. Y bueno, soy chileno, ustedes saben la situación que hay en Chile y bueno, producto de eso se canceló mi vuelo y no pude llegar al Congreso, así que me dieron la posibilidad de presentar en línea. Hubieron problemas técnicos y no se pudo hacer, así que yo ofrecí la posibilidad de grabar la charla y subirla por el canal, y el video sería adjuntado en alguna parte del Congreso para que quede publicado. Así que bueno, eso, esta charla puede ser un poco técnica, porque es de mi área, va a salir en inglés para la gente del Congreso, pero pueden poner subtítulos en español. Voy a tratar en algún momento subir los subtítulos. Y bueno, de todas maneras, si el tema es demasiado técnico para tu interés, te dejo invitado para el próximo video, que ya está próximo a subirse, que vamos a hablar sobre mecanismos de control social que ocupan los militares para tratar de controlarnos a nosotros, que por ejemplo el toque de queda, cómo funciona el adoctrinamiento de los militares, todo eso explicado con un modelo físico que es el modelo de Ising para imanes, ¿ya? Así que seguro si eres físico o matemático lo conoces, y si no, prepárate para el próximo video verlo. Voy a pasar al inglés. Okay, I will start to speak in English now for the members of the Microfluídica Congress. I wanted to tell you that I really wanted to participate in this Congress. I understand that the Microfluídica is the developing area with the potential to solve a lot of technical problems from the point of view of biology and medicine and the industry in general. It could be a great if Argentina, Brazil, Chile and other countries could develop an industry based on microfluidic devices. That is why I was very excited to know that is being investigated in other places. But for that, Chile needs to be free first. Chileans are fighting for our rights, and the battle is not easy with the soldiers on the street without control. The national press media were bought by President Sebastián Piñera, and so the only way for people to know what is happening here is through the foreign press and the social networks. Please, I don't ask you to spread this video. I ask you to dialogue about this subject, talk with authors, let the world know what is happening in Chile, discuss the issue with your families and with your friends. We need the people of the world to know that Chile is awake. Chile is not in war, and we want the armed force off the street and the resignation of the President Piñera. Thank you. I will speak about of my program. Hello, okay. I will speak about the formation of quasi-2-dimensional drops traveling in a microchannel. My name is Pablo Mardones. My advisor is María Luisa Cordero. We are of the Universidad de Chile, Facultad de Ciencias Físicas y Matemáticas, Departamento de Física, Laboratorio de Microfluídica. I want to agradecer a Fondesit, a Facultad de Ciencias Físicas y Matemáticas, a Proyecto Milenio y a CONICYT por la beca que me ha permitido estudiar. Okay, first I will speak about the experimental setup. In the left side, we can observe this a microscope with a microchannel in this part. Okay, this part we have a microchannel devices, and the microchannel devices is over a stage, a motorized stage, controlled by this object that is the controller. We can program the motorized engine, the motorized stage with a lab view or with this joystick of here. Okay, the scheme of the microchannel is here, and the microchannel have two entrances, one for water and one for oil. We have here two syringe pumps. This syringe pump inject oil and water in this scheme, and here have a out of fluids. Okay, the dimensions of the experimental setup. Well, we have a microchannel with three parts. First, we have the entrance with oil and water. Here, the oil is separated by this system, and in this part, in the second part, we have here we have the formation of the droplets, the oil flow, size the arm flow, and form the droplets that is traveling by for this part. This part is the section of measure. In here we have a dimension of 591 micrometers of width and 44 micrometers of depth. The size of the large is 3 centimeters, and we have oil with viscosity is 0.186 Pascal per second. The mean surface tension of the water is oil, and oil interface is 2 millinewtons per meter. So when the droplets is formed traveling by this channel, and this channel for due of the dimensions is very flat. Okay, the oil and water flow for here, and we can control of the experiment, and we have a section very flat. The deep is H is 44 micrometers, and here is about 600 micrometers. So the channel is very flat, and with the syringe pump we can control only a flow, the oil flow and water flow, but these parameters are not important, or are not the most important parameters of the experiment. Other parameters more important are the capillary number and the aspect ratio between water and oil. Why? Because capillary number is this number of here that it depends and control the relation between the effect of viscosity and the surface tension. And why is important these parameters? Because the viscosity, the effects of viscosity are due the deformation of the droplets. Okay, and the surface tension is the stress, or is the part of the stress tensor that can or try to keep the form of the water drops. Okay, here is the viscosity relative, the surface tension, and the mean velocity of flow. So to calculate this number, we use the velocity is equal to total flow. I don't know how do you say dividido. Dividido el área. Okay, and the aspect ratio control the relation between water and oil in the microchannel. So with this parameter, I can control more or less the distribution of the dimension of the water drops. And here with this, we can control more or less the deformation of the droplets. So what kind of variables we can observe? Principally use the confinement. The confinement is the relation between the diameters with the height or depth. We have or other dimension of the channel. We use two kind of definition of confinement. The first is delta. We compare with the depth, the dimension, the droplet with the depth, and this confinement compare the dimension of the droplet with the weight of the microchannel. In this kind of microchannel, we have a confinement droplets normally, and for the due of the deformation, due of the confinement, the droplets are not spherical. Are very compressed and take a form of a coin or a pancake. Okay, so you can think this like a quasi two-dimensional droplets. Okay, because the deep or height are not important. To characterize the formation of the droplet, we use the composition in Fourier mode. First, we use using image analysis, detect the border of the droplet, and in this case, and consider this like a periodic a row with periodic conditions. Okay. So here we have a rope between here and cut here, and I strike this rope, and over this rope we use the decomposition in Fourier mode. These Fourier modes describe the different waves or maneras of the formation the droplets. For example, the zero mode is describe the dimension of the droplets. Okay, the zero mode is the mean radio of the droplets. The first mode, when considered odds even modes, is in here in blue, and modified a little the displacement of the droplet of the center mass. Okay, the second mode is most important because the second mode is in green, and when it's positive, describe a deformation in the x-axis, and when it's negative, describe a compression in x-axis or a deformation in y-axis. Okay, and the third mode have three crests or three peaks here and here and here, and when it's positive, produce a bullet form of droplets, and when it's negative, produce drops with tails. Okay, so now we use consider also the odd modes. Okay, even and odd modes. Okay, for example, here we have an anti-owl experiment with the droplets recently formed, and here the droplet is formed, is cutter for the oil flow. Here is recent formed, and here the droplet is relaxing. Okay, it's relaxing point, and the effect of the flow is deform the droplet when the droplet is traveling by the microchannel. To describe this, we use the zero mode, describe my radio, and here we have in blue the first mode that is very little, And the second mode is in green because and positive here because we have the horizontal deformation, and here is this point without deformation, and here is deforming by the microchannel in the y-axis here. And the first mode we have negative because here we have a little tail, and after lows this tail. Okay, here you can observe a big droplet traveling by this microchannel, and it's a big droplet, and this droplet is deforming during her travel. And when the droplets are little, we have this kind. For little droplets, we have little deformations or no deformations. Okay, here we have a graph, a plot with the evolution of the different modes. The first 5 even the first 5 even modes. Okay, here we have the most important is the second mode is evolving, and the third mode is here. Well, here is positive because the droplet have a little form of bullet, and here is we have a droplet more or less in equilibrium. Here suddenly pass something that I know why, but the droplets is begin to do strange things. Okay, so we use this point to consider the deformation in equilibrium. Okay, the steady state of deformation. For this sequence of experiment, we measure different oils in different conditions. We use 3 conditions keeping the aspect ratio flow like a phi. For example, here we have 15 part of oil and 1 part of water. Here we have 25 parts of oil between 1 part of water. Okay, and here we have a experiment with condition keeping the aspect ratio, and here is keeping the capillary number of total flow. And well, we try to analyze the statistic of the deformation and what are others measures. And here we have the distribution of the confinement or size of the droplets, and the dependence of the aspect ratio, the relation between the oil and water in the microchannel. You can see that we have a distribution of size, or a distribution of ratio, or distribution of confinement. It depends of the aspect ratio, of water and oil, but it's not a beautiful graph. It's not a dependence clearly. Okay, here we have a capillary. Okay. We have a set of experiments keeping the capillary number. Okay, but we have a this plot say me or something that is very important with the ratio of the droplets is not
easy to control. You can control a distribution of the radio of the droplets with the relation between water and oil injection. Here we have experiment the dependence of the different modes, the even modes, and with the confinement, the dependence of the mode is depending the relation with the modes and the mode with the confinement is very clearly we can control the modes, the different modes with the radio, okay, and the deformation of the modulus of the decomposition further, it depends only with the confinement, okay. The size of your droplet define your deformation. Here we have other kind of represent this information, because we have 5 modes of deformation odd and 5 modes of deformation of even deformation. So here we use a global measure of deformation, the root mean square of the different modes of Fourier. So when you use this description, we have a beautiful graph, a good description, and you can see that the global deformation or RMS deformation, it depends clearly of the hair size. And when we try to describe a power law, we have this kind of power law. The deformation of the global deformation is depending of the confinement power for potency. Okay, we have a linear dependence. Okay, it's not linear, but it depends on the fourth power law. Well, so something, no, algunas conclusiones. This is important that the decomposition by mode seems to be a good tool to measure drops deformation. Okay, this is a good tool. And the deformation of the drops in equilibrium only depend on the confinement of the drops. Okay, and you can't control the deformation of the droplet only with the oil flow and water flow. The oil flow and water flow only can control the distribution of the size of the droplets, but you know the deformation the droplets with good precision when you know the size of the droplets. The size of the droplets define the deformation in a steady state. The amplitude of the steady state Fourier modes do not follow clear tendency, but the steady state mean square root deformation follow the power law, this power law of here. Okay, the DRMS is proportional to the confinement of fourth power law. Thank you for your attention. Well, if you have different questions about this presentation, you can write there down in the commentaries, and I can answer you when I have a little time. Thank you, and nos vemos en nuestro próximo video. No olviden de seguirnos. Thank you for seeing me, and don't forget subscribe to this channel, and thank you for your attention already. Okay.